Hello students. Last session we were seeing what is Ampere's law and we were seeing the two applications of Ampere's law. One is the infinite line current, the other one is the infinite sheet of current. So first a recap we'll do. What is Ampere's law? Ampere's law is nothing but the closed integral H dot dl is equal to the enclosed current. That is Ampere's circuit law. Now we'll see the third application of Ampere's circuit law. So it is infinitely long coaxial transmission line. So you consider an infinitely long transmission line as shown in the figure, consisting of two concentric cylinders having their axis along the z-axis. So you have an inner circle and the Amperian path will be L1. You have an outer circle, the Amperian path is L2. And you have a third circle, the Amperian path is L3. And you have a fourth circle, the Amperian path is L4. So we have 4 Amperian path. And you have considered the axis along the z-axis. And you can see the two currents over here. You know that if you put a small circle and inside if you put a dot means, so the current is out of the page. If you put a cross and then a small circle means the meaning is the current is into the page. Okay, so this is the diagram description. So we can see there is an inner conductor which has a radius of A. So see here, there is an inner conductor which has a radius of A and that carries a current I, while the outer conductor has a radius B and the thickness T carries the return current minus I. I'll repeat again. So the inner conductor, this is your inner conductor, which has a radius A and carries a current I, while there is an outer conductor is also there and its inner radius is B. You can see from the center point, the inner radius of this outer conductor will be your B. And the outer conductor is having a thickness of T, which carries a return current of minus I. So we need to determine the magnetic field intensity H everywhere, assuming the current is uniformly distributed on both the conductors, that is inner conductor as well as the outer conductor. So we need to apply the Amperian path for each of the 4 possible regions. So we have 4 Amperian paths, L1, L2, L3 and L4. So first we need to see the limits between, that is the radius rho lies between 0 to A and the rho lies between B to B plus T. So up to the inner side of the outer conductor will be B and the thickness is T. Therefore, at this point, it will be B plus T. So we need to find the radius rho between 0 to A and also between B to B plus T. So we'll see the equations now. So there are 4 Amperian paths are there, I said, L1, L2, L3 and L4. So the first Amperian path will have a radius of rho is equal to rho lies between 0 to A. And the second Amperian path will lie between the radius. I'll show the figure also. So the first Amperian path will have the radius rho, which lies between 0 to A. And the second Amperian path L2, which has a radius rho, which lies between A to B. This is A and this is B. So A to B. And the third Amperian path will have the radius rho between this point is B and this point is B plus T, because the thickness of the second conductor is T. Therefore, this point will be the B and this point will be the B plus T. So the third Amperian path will have the radius rho lies between B and B plus T. And there is a fourth Amperian path is also there where rho is greater than B plus T. That is what written there in this equation. So for first region, we'll see what is the applying the Ampere's law. For the first range of values, we'll see. So for the first region where the radius rho lies between 0 to a, so for the Amperian path L1, H dot dl is equal to enclosed current. This is nothing but your Ampere's law. It is nothing but J dot ds. That is volume current density. We have represented in terms of volume current density. Since the current, already I said you, when I start this application, the current is uniformly distributed. So J is equal to, we can write the J as I divided by pi a square into AZ. As I said you, it is along the Z axis, that why its unit vector is AZ. So I can write the current density as I divided by pi a square. Pi a square is the circumference of the circle. So, and ds can be represented as, ds is the differential surface area. That differential surface area is with respect to the change in rho, with respect to the variation in the z axis also. So rho d pi d rho az. Now in this equation, I enclose, substitute the value of j as I pi a square az and substitute the value of ds as rho d pi d rho az. So when you substitute it, we need to put accordingly the integral values. So the integral value will range from, will be for the pi value as well as for the rho value. So since we have taken the region, the first region where rho lies between 0 to a, I'll write integral with respect to pi, the limits will be 0 to 2 pi. And then with respect to rho, since the region is 0 to a, the limits will be 0 to a. So taking the constant terms outside, I divided by pi a cube, integral pi lies between 0 to 2 pi and integral rho lies between 0 to a, rho d pi and t rho. So when you integrate d pi, the value will be pi. When you integrate d pi, the value will be pi. When you integrate rho square divided by 2 with respect to rho, so you will be into d rho, you will be getting rho square by 2. So that is what I have written here. So rho square divided by 2, when you integrate it with respect to rho means it, into d rho, you will get rho square by 2. When you integrate d pi, it will be pi. And then you substitute the values of rho and d pi, you will be getting enclosed current will be equal to I rho square divided by a square. Rho square as it is I have retained. Actually for rho I have to change it as a square. So I want to make clear rho is the radius from the center of the circle to a particular point and a is the radius of the specific region. So I have used the two different words, rho and the a square. If I use for rho, a means both will get cancelled, but the meaning is different over here. So I have retained the rho value as rho only rather than substituting as a. So I enclosed will be equal to I rho square divided by a square. So we know that your h is nothing but I divided by 2 pi rho into a pi. So just we can equate these two equations. Therefore, we'll get h integral L dl will be equal to h pi 2 pi rho, just cross multiplying and doing, which will be equal to this enclosed current. In this, if you rearrange, what you will get, I is equal to h into 2 pi into rho. This is also enclosed current. We have another equation for enclosed current, I rho square by a square. An enclosed current is also equal to h into dl. So all these three enclosed current, I'm just equating because all are enclosed current. So h dot dl will be equal to, rearranging this equation, h by 2 pi rho, and this equation, I rho square by a square. Therefore, we can conclude your h pi is nothing but I rho divided by 2 pi a square. Okay, because here one rho and here one rho will get cancelled because both we have same terms on both the left hand side and right hand side. Therefore, we can conclude h pi is nothing but I rho divided by 2 pi a square. Now, for the second region, we'll see where the rho lies between A to B. Okay, so we can see here. So we can see here for the second region, rho lies between A to B. So that is, we are going to consider the path L2. Therefore, the ampere in path L2 H dot dl is equal to enclosed current. Enclosed current, nothing but we can write it as simply I also. Therefore, I is equal to, since the second path lies between 0, A to B, I can write H is equal to, it's a circle one, so H 2 pi into rho. Therefore, H pi will be equal to I divided by 2 pi rho. Then for the third region where rho lies between B to B plus T, that is the ampere in path L3, we can write ampere in path L3, that is the closed integral H dot dl is equal to H pi 2 pi rho. Why the 2 pi rho means it is the circumference of the circle will be 2 pi and it ranges with respect to the rho. So that is nothing but the I enclosed current. Okay, now we'll see for the last one. So I enclosed current for the third Laplacian path will be I plus integral j dot ds. Why this I plus means you can see in the diagram till the inner circle of the second conductor you have found. Up to this you have found what is your I. You want to know what is the current I for this point. Okay, at this point you want to find. So what I can do what I have found till here plus what I'm going to find for this thickness. That's what I have written over here. So I can write I enclosed current for the range rho lies between B to B plus T as I plus integral J dot ds, where J is the current density for the outer conductor and it is along the minus AZ direction. So J can be written as minus I divided by pi a square. That is what the formula we have seen just before, no? The same formula only. It's not minus I, it is plus I. Plus I divided by pi a square. Here we have written. You can just recollect over here. J is equal to I divided by pi a square AZ. This is for the inner circle we have written. But the outer circle is the current flowing in the opposite direction. That's why the unit vector AZ is minus sign. It is not for the I, it is for the unit vector AZ. So you get I divided by pi a square. In the place of a square, I have written B plus T. A square is nothing but the distance between your outer circle of the second conductor to the inner circle of the second conductor. So B plus T the whole square minus B square. Okay. Now I'm just splitting and writing this equation. So I enclosed current will be equal to I minus I divided by pi B plus T the whole square minus B square, and integral lies between pi and rho. So pi ranges from 0 to 2 pi and rho ranges from B to B plus T. And your I varies for, and your Z, A Z unit vector varies with respect to rho, d pi and t rho. So taking I as common, we can write enclosed current is equal to I 1 minus rho square minus B square. That means after integrating this term, you will get rho square minus B square divided by T square plus 2BT. So this equation 5 So this equation 5, equation 6 will become H pi dot 2 pi rho will be equal to I of, that is I enclosed current is nothing but H dot dl, right? Instead of H dot dl, what do we have? H pi into 2 pi rho. That is what I have written, equal to, the right hand side remains the same. I of 1 minus rho square minus B square divided by T square plus 2BT. Therefore, h pi, bringing this 2 pi rho to the other side, in the denominator, we get h pi is equal to I divided by 2 pi rho, 1 minus rho square minus b square divided by t square plus 2bt. And you know that there is one more ampere in path L4. For the path L4, your rho is much greater than P plus T. Therefore, your currents will get cancelled. That is, integral L4 H dot dl is equal to I minus I, which will be equal to 0. Therefore, your H pi will be is equal to 0. For concluding, your magnetic field intensity H for the first range where rho lies between 0 to A will be I rho divided by 2 pi A square into A pi. And for the second range where rho lies between A to B, the H value will be I divided by 2 pi rho into A pi. And for the third region where rho lies between B to B plus T, it is I divided by 2 pi rho, 1 minus rho square minus B square divided by T square plus 2bt. And for the fourth region, rho greater than B plus T, your magnetic field intensity will be equal to 0.